finished lectures 4, 5, and 6, which deals on organic acids and bases. So to help you understand some of the concepts that were highlighted in lecture 4, 5, and 6, I'm trying to solve some problems that are related to organic acids and bases. The first problem set, these 4 problems, it's asking you what are the products of these bases when they are reacted with a strong acid like sulfuric acid. Sulfuric acid is a very strong acid which can easily donate a proton because of its strength. So let's see here. In this compound, the most available electrons are stationed on oxygen. So the lone pair of electrons that are on oxygen are acting as a base. So we can call those are Lewis bases, for example. So the base is the result of the electrons that are on oxygen. So those are the basic sites. So now I'm representing a proton from the sulfuric acid, which is this, and always gives 1 proton. When it is reacting, this pair of electrons in the direction would take up that proton. And the product looks like a plus. And since 1 proton is transferred, the sulfuric acid generates its conjugate base like that. Because this is sulfuric acid. That is the sulfuric acid. Now, in this case, this is a base, obviously, and this is the acid. And here is the conjugate acid, and this is the conjugate base. In all of the cases, that anion would be the conjugate base. Next to that, the lone pair of electrons on nitrogen are what makes this compound a basic compound. Therefore, lone pair of electrons on nitrogen are responsible for the reaction. So if you have H plus from the sulfuric acid, and the electrons would pick up 1 of the protons to generate the conjugate acid, which is NH3 with a plus and the same conjugate base. So this is just to show you where is the basic site and also what is actually happening in the reaction. Where is the basic site? Here also now, if you just look at this pair of electrons, the lone pair of electrons, this would be your base. So you cannot just assume there are basic sites on this compound except the lone pair of electrons. By definition, for example, if you remember, Lewis base is something that can donate a pair of electrons. Therefore, now, in the reaction, this pair of electrons would grab that proton from the sulfuric acid, which is a very strong acid, to protonate the oxygen. So that is a protonation reaction. This is protonated now because a pair of electrons has been transferred, OCH3. Now that's the conjugate acid. That is a conjugate base. In this case, obviously now, you remember the lone pair of electrons on nitrogen are the ones which are acting as a basic site. So that's the base. The base would take up that proton, and the product looks like a protonated nitrogen here with H added and CH3, which was already there. Now, I want to remind you that whether a lone pair of electrons on oxygen or on nitrogen they differ in terms of their basicity. Electrons on oxygen are not as basic as the electrons on nitrogen. The reason being, the electrons on oxygen are not easy to be donated as compared to nitrogen. They are loosely bound in nitrogen than in oxygen. Therefore, all lone pairs that are on nitrogen or nitrogen containing compounds are more basic than oxygen containing compounds. So if we were to compare, for example, exactly these two in comparison, the basicity of this oxygen versus the basicity of electrons on this nitrogen, this is a stronger base. Stronger base. This is comparison between the two. Weaker base as compared to this. The reason being, I will repeat this again, the lone pairs on oxygen are tightly bound to oxygen because of it is more electronegativity. But here, since nitrogen is not as electronegative as oxygen, the lone pairs can easily be donated to the acid, or they can grab, or they can get easily protonated. Therefore, nitrogen containing compounds are more basic than oxygen containing compounds. This is as a side note so that you understand this in the future lectures. Oxygens, the lone pairs on oxygens are less available than lone pairs on nitrogen. This is a very important concept. That's why this is a stronger base than the alcohol. So this is in general, this is an amine compound, this is an alcohol compound. So alcohols are lesser basic than amine compounds. So this is an alcohol. We'll discuss this in functional groups. This is OH containing, which is alcohol. They are less basic, their oxygen is less basic than the ones contained in the amine compounds, such as nitrogen compounds, because those lone pair of electrons on nitrogen are easily available. Okay, let's continue solving some problems. And in this problem, you are asked, what are the products of this acid-base reaction? So the acid-base reaction is important for you to know which one is acting as an acid and which one is acting as a base. So if you come to this problem, for example, the carboxylic acid, COOH, shows you this proton is very acidic. And as our discussion before, this pair of electrons can take from nitrogen as a loose base some protons. Therefore, this acts as a base, and this is the acid. Now, the product of this reaction, or the equilibrium, can be such that the proton would be abstracted. Remember the direction where the pair of electrons would take up the proton. Therefore, the product looks like one of the protons on the carboxylic acid is taken out, and you are forming NH4+. So if you just assign this would be the conjugate base, and this is the conjugate acid. Now, if you just look at this, whether the reaction could go forward would be indicated. For example, the pKa value for this carboxylic acid is about 4.8. And the conjugate acid that is generated has around pKa of 9.2. Therefore, it is going from a stronger acid relative to that to a weaker acid. Therefore, the reaction mainly goes to the forward direction. Let's continue on the second one. Still, this is obvious. This is a carboxylic acid, similar to that, except this is methyl, this is benzyl group as a substituent. So this is an acid, and this is the base. The base is called sodium bicarbonate. That is sodium bicarbonate. So sodium is a spectator ion. The negative charge resides on HCO3 minus. Therefore now this minus sign on the overall this base can abstract this proton. This proton is a very acidic one. You don't take any proton from this, but rather this is the most acidic proton on the carboxylic acid, on oxygen. Now the product looks like CH3, similar, exactly the same, except it is an acetic acid or acetate base, conjugate base. This is a conjugate base, and the product is a sodium plus H2CO3. This is the conjugate acid. So if you just look at this is a reaction in the forward direction. You are generating a conjugate base and a conjugate acid. Remember, this is the acid and that is a base. This is an alkyne where you have sp hybridized carbons. If you remember, hydrogen on sp hybridized carbon has acidic property. This is a proton that is more acidic because it is directly attached to a carbon that is sp hybridized. So this carbon has a negative nature where it can carry the negative charge on it. Here you have a sodium amide, which is a base. Remember, this is NH2 minus. It is called amide base. Sodium is just a spectator ion like this, so the base is actually this in the parentheses. So now abstraction would happen to this proton, would be abstracted by the negative charge on amide, and the product looks like CH3, C minus, a pair of electrons on plus NH3. So if we were to classify this would be the acid, this is a base, and this is a conjugate base that is generated. So because it has a negative charge on it, now it's acting as a base. Here is the conjugate acid. Now, continuing in the same fashion, we have potassium hydroxide. Remember, potassium hydroxide, like sodium hydroxide, is a strong base with OH minus. So the base is the OH minus. Here on this alcohol, the only acidic proton you can see is, these are not the acidic protons. The acidic proton is the one which is directly attached to oxygen. Therefore, this proton would be abstracted by the OH minus from the base. And then you would create CH3, CH2O minus, the conjugate base, plus just water. That. So therefore, now this is the conjugate base. Remember, you always create a conjugate base and a conjugate acid. Now water, in this case, is acting as a conjugate acid. In this reaction, it is a conjugate acid. Here, this is the acid, and here is the base. So one important point I want to highlight to you would be acidity and basicity of a certain compound is relative to what kind of reaction you are undergoing. Here, for example, water in some other reaction could act as a loose base. But here, as a byproduct of this reaction, water is a conjugate acid. We have a nitrogen-based amine, which is, amines are always basic. because you have a lone pair of electrons on this, and you have sulfonic acid. I want to remind you specifically to this because it is attached to a sulfonate group. This OH minus is very acidic because the resulting conjugate base can be resonance stabilized. Here also, why these are forming in the right direction is this negative charge can be resonance stabilized. So the acidity also comes from that fact. Therefore, now this lone pair of electrons would pick up that proton. These are lone pair, so this is a loose base. So this is a base. This is an acid. I want to remind you the pKa of this proton is close to -7. It's very acidic. So it's a sulfonic acid. It is pKa is close to -7, which is equivalent to having a mineral acid such as hydrochloric acid. Now, if you just write the product for this, the product looks like CH3 to NH2 plus, because one proton has been transferred, and plus one proton has been abstracted from that, CH3 SO minus. Therefore, now you have, this is the conjugate acid, this is the conjugate base. The reason why the forward direction is much more favored is you are generating a very stable conjugate base that is resonance stabilized. You can draw a resonance structure for the product that is formed. So it's very stable. So the product is driven to the right direction in this acid-base reaction. Therefore, in determining the reaction, whether it goes forward or backward, you should also consider how is the conjugate base or the conjugate acid that's being formed in the product side is stabilized by a resonance, by inductive effect, or all of the factors that we mentioned in the lecture series. Here in this problem set, you'll be calculating pKa values and see which one is the most strong acid. So as you see, the Ka values are given, and the salt or they look like a conjugate, all of them are acids here. That's why you'll be calculating the Ka values. Based on the Ka or the ionization constant, we can tell that the strongest acid is this, because high ionization constant Ka value can immediately show you this is the strongest acid. The next strongest acid would be B, which has a Ka value or the ionization constant 2.3 times 10 to the minus 5. The weakest acid is the top one with a Ka value of 4.7 times 10 to the minus 10. But in any case, the problem asks you to also see or calculate the pKa value, which is very easy mathematical manipulation, where pKa equals the minus log of the Ka for all of them. Therefore, now, for example, for compound A, the pKa value equals minus log of 4.7 times 10 to the minus 10. So when you calculate, obviously you can use your calculator, and the result is, what you have to do is, that would be 10 minus the log of 4.7, which gives you a pKa value of 9.23. You can check this on your calculator. So basically, you are having almost, this is a base. As you see, it's not that a strong acid. Obviously, we have already seen that's the weakest acid with pKa value of 9.23. So similarly, when you calculate for pKa value for this one, the pKa is equals to the minus log of 2.3 times 10 to the minus 5. So this is an easy calculation with a logarithm from a calculator. You would end up calculating 4.64 is the pKa value. In the last one, the pKa value should show or give us a very small number as compared to the others. But large K constant is for that trifluoroacetic acid. 5.9 times 10 to the minus 1, which becomes to be 0.23. A very low pKa value means a strongest acid. This is the strongest acid. So if you just look at the comparison, like what I have already said, 0.23 followed by 4.64 followed by the least acidic one is the protonated amine. The next protonated amine is attached to a phenyl ring directly. It has 4.64. If you just look at the difference between these two, there is one more carbon between the pi electron system as compared to this one. This one is directly attached to the pi electron system. Here, an important concept I want to highlight for you would be, this is an acid. If we were to compare it, for example, with CH3, COOH, which is acetic acid, versus CF3, COOH. Important comparison here is there is an important, both are resonance stabilized when the proton is gone. So that's not what the difference is. pKa value, for example, for the acetic acid is close to 4.5, 4.8, let's say. But the trifluoroacetic acid has 0.23. Very big difference in terms of acidity. The trifluoroacetic acid is very, very strong acid. If you remember some of the factors that affect the acidity or basicity of a compound is inductive effect. So the inductive effect of fluorine, having instead of hydrogen, you have fluorine on trifluoroacetic acid. So fluorine induces a very significant inductive effect to stabilize the conjugate base. So this is inductive effect. Why trifluoroacetic acid is much more strong acid. 4.8, 0.23. That is significant, almost 20 more times more strong acid than acetic acid. So remember, there are different factors that affect the acidity of a compound. One is inductive effect, the other is hybridization effect, the other would be element effect, and so on. So these were discussed in lectures 4, 5, and 6 in previous sections. So these are simple calculations to show you how pKa measures acidity. Here, the ionization directly is a normal number that the equilibrium constant, Ka, the acid dissociation constant, is just changed to a pKa or a logarithm scale. Otherwise, they measure the same thing. So even if you just look at here, the highest ionization constant, high ionization strongest, is the highest number, strongest with high ionization constant, So the higher the ionization constant, the stronger the acid would be. But in the reverse, the lower pKa value means high ionization constant. So in this problem set, the question is which direction the equilibrium can be shifted. That means you have to understand what the products look like, and then based on the pKa differences, you would predict which side is the equilibrium can shift. This is all acid-base reactions. Obviously the acid and the base. And first what you have to do is you have to just put the products first and see whether that equilibrium is favored in the right direction or left direction. So here, this is a trifluoroacetic acid, the acid, and you have a base, which is an etoxide with a lone pair of electrons on it. So what it does is this base would abstract that proton, exactly that, and you would have CF3 COO minus plus the alcohol formed by getting one proton. So that's the product. In the next one, this is the base, the acid, and this could act as a base. That means Cl minus is supposed to be a base, let's say. So if Cl minus abstracts H, it would form a CH3 CH2 COO minus plus HCl and sodium plus. So that's what is predicted. We'll check whether that is right or wrong, which side the equilibrium would shift, and by showing the arrows. Here you have tert-butanol. This is an alcohol. In this case, it's acting as a base because you have a very strong acid here, which is an acid, sulfuric acid. It can transfer its proton to protonate this. So the product looks like CH3, 3, COH2, a plus, because it acquires one proton, and you would have the conjugate base, obviously, is this. In the next reaction, here this is acting as an acid, specifically that proton, and here is a base because sodium is a plus 1, HCO3 is a minus, therefore it would pick up a proton from there. So we would have O minus plus a sodium plus, obviously, plus a carbonic acid by getting one proton. In this case, this is acetylene. Remember, sp hybridized carbon, and the hydrogen would be, this one is acidic. And we have a lithium carbon, these are called carbon ion. Carbon ion are strong bases, carbon ion are strong bases because this is a very unstable negative charge, so it rarely would accept a proton. So the reaction would give Hc, C minus, with a pair of electrons, plus lithium, obviously there, and CH3, CH3, because one proton has been transferred to this. So you have CH3, CH3 is formed. Now, to indicate whether the reaction moves into forward or backward, you need to understand the pKa value of the acid and the conjugate acid. By comparing the two pKa values, you cannot go from a very weak acid into a strong acid. That equilibrium is not allowed. So I'll demonstrate by saying that trifluoroacetic acid, the pKa value is about 0.23 pKa value. How about the alcohol, that's the conjugate acid, that's formed? It has a pKa value of around 16. So you need to refer to a pKa table to see what values you are for the acids. So I'm going from a very strong acid to a very weak acid. So the equilibrium actually shifted to the right. That's correct. A very small amount equilibrium to this. So most of the reaction can happen in the forward direction because you are going from a very strong acid to a weak acid. That's how the reaction should proceed. In the next one, close to this acid, which is a carboxylic acid, carboxylic acids are close to 5, 4.5, 4.8, about 4.8 if we say pKa value. And now you are trying to generate this acid, which is a pKa of -7. So this reaction actually doesn't go in that direction because starting from a very weak acid, you are going to a very strong acid. Actually, the equilibrium actually is not in that direction. The equilibrium is more to this direction and much less to that direction. So the equilibrium has to be backward. So almost the reaction doesn't happen. In this case now, you have a tertiary butanol. This is an alcohol. Alcohols generally are about 16, 17 pKa values. So you need to have a qualitative understanding for each functional group. Since this is an alcohol, let's say the pKa values are around 16 to 18. Okay? Now, the conjugate acid that is formed, this cation, very unstable cation, is pKa of, I think, close to -3.8, a very strong acid. So the equilibrium actually doesn't go to that direction. The equilibrium actually is not in favor of forming a strong acid. Actually, the reaction is in equilibrium to the left side. Next reaction, which is a phenol. This is an alcohol, but it is attached to a benzene ring. Therefore, even though it's an alcohol, the pKa value goes as low as 10. So it's a kind of more acidic than regular alcohols because of the ring here. So pKa value is around 10. So from pKa value of 10, we are going to a carbonic acid. Carbonic acid is pKa value for the first proton is about 6.4. So remember now you are going from a weak acid to a stronger acid here. So the equilibrium actually, even though the pKa values are not that much big difference, the pKa shows us the equilibrium actually should be shifted more to the left than to the right. Because you cannot go from a very weak acid to a very strong acid based on pKa value. So here it is very important for you to practice to know pKa values. You can refer to pKa tables, but you should apply them in a way that to predict an equilibrium reaction of acid-base reaction. Here, the pKa for alkynes or such a system in acetylene, let's say it is pKa of 25 for this or that proton. You have here a carbanion, a very strong base, and generating conjugate base, and this acid is generated. When we say acid, it's a relative term because it accepts one more proton. So the pKa for alkanes, or just sigma bond, carbon-carbon bonds, alkanes, pKa is very, very high. That's pKa 50. So this is pKa 25, it is going to pKa 50. The reaction actually is favored in the forward direction, very little into the backward. So this reaction goes forward into the right direction based on the pKa difference. So remember, the whole point of this exercise is, one, to understand what is the conjugate acid that's formed, and two, the pKa value of the conjugate acid should be larger than the pKa of the starting acid. Otherwise, the reaction would not go in the forward direction. So it is always you go from a very weak acid from a very stronger acid to a weak acid. That's how the equilibrium shifted. Otherwise, it goes to the backward direction. So you were able to determine the equilibrium of the reaction or the direction of the reaction based on pKa values. pKa values are very important to determine the strength of the acid and also to determine the equilibrium of the reaction.